How does the second law of thermodynamics relate to information theory? Have you ever wondered how the laws of physics connect with the way we understand information? Today, we will look into the fascinating relationship between the second law of thermodynamics and information theory. The second law of thermodynamics tells us that in a closed system, disorder, or entropy, can only increase or stay the same over time. This means that energy transformations are not always efficient, and some energy is lost as heat, leading to more disorder. On the other hand, information theory, created by Claude Shannon, introduces the idea of information entropy. This concept measures the uncertainty or randomness in a set of data. While both types of entropy share the same name and some mathematical similarities, they come from different fields. One is rooted in physics and the other in communication theory. So, how do these two ideas connect? At the core, information is a physical entity. According to a principle known as Landauer's principle, when we erase or process information, we must expend energy. This energy use increases the physical entropy of the surrounding environment. In simple terms, when we organize information, we cannot escape the laws of thermodynamics. Any reduction in information entropy, which makes data more ordered, must be offset by an increase in physical entropy somewhere else. A classic example that illustrates this connection is Szilard's engine. In this thought experiment, knowing the position of a single gas particle, equivalent to 1 bit of information, allows us to extract useful work from the system. However, even in this scenario, the total entropy of the entire system and its environment does not decrease, which aligns with the second law. Recent studies have taken this relationship further, proposing a second law of information dynamics. This idea suggests that in certain information systems, information entropy can remain as constant or even decrease. However, this decrease must be balanced by an increase in physical entropy in the environment, ensuring that the second law of thermodynamics is not violated. This connection is especially important in practical fields like computing. When we work to reduce errors and organize data, we lower information entropy. Yet, this process requires energy and generates heat, which adds to physical entropy. The same principle applies in biological systems, where processing genetic information comes with thermodynamic costs. Understanding this relationship helps us grasp the energy costs associated with information processing. It also highlights the fundamental limits that physics imposes on computation and communication. The second law of thermodynamics and information theory are intertwined through the physical nature of information, showing us that changes in information entropy are closely linked to changes in physical entropy. This connection is essential for understanding how we handle information in our world.